It hurled iron bolts silently across the battlefield without warning. Its projectiles could pierce two men, their shields, and even the wall behind them. And yet, most people today don't even know its name. This was the Roman ballista, a weapon so precise, so terrifying, that it shaped the battlefield for centuries. Welcome to your daily history channel, Great History EN, where we bring you incredible stories of ancient warfare every single day. We're proud to be part of a growing community of history lovers, and if you're new here, hit that subscribe button and help us reach 40,000 subscribers so we can keep sharing epic battle stories every single day. What made this machine so advanced? Why was it feared by enemies and revered by engineers? And how did it vanish from history when so few people today know it helped shape the weapons we still use? Let's find out. Where did the ballista come from? Though perfected by Roman engineers, the ballista's story began centuries earlier in the intellectual crucible of classical Greece, in the workshops and laboratories of Hellenistic science. Before it became a weapon of empire, it was a device of innovation. The earliest ancestor of the ballista was a curious contraption known as the gastrophetes, or belly bow. Invented in the 5th century BC and described later by Heron of Alexandria, the gastrophetes functioned like an oversized crossbow. It was cocked by pressing it against the stomach and allowed the operator to launch bolts farther and with more power than a traditional bow. Crude by later standards, it was the first step toward something revolutionary, storing mechanical energy not in the limbs of a bow, but in tension devices designed for force multiplication. But the real leap came a century later, in the fortified city of Syracuse, where tyrant Dionysius the Phrygian did something no Greek leader had done before he hired full-time military engineers. Under his watch, Greek craftsmen experimented with torsion power, using twisted bundles of sinew or hair to power machines that could hurl massive projectiles with terrifying velocity. Thus, the first true ballistae and catapults were born, machines that would forever change the face of siege warfare. By the time of Philip II of Macedon and his son Alexander the Great, artillery was no longer just for sieges. Lightweight torsion engines, early mobile ballistae, were brought into the field. During the siege of Tyre in 332 BC, Alexander used them not only to clear defenders from the city's high walls, but also to protect siege towers during their final advance. The historian Arrian later described these machines firing bolts with such force and precision that they could pick off enemy commanders at a distance. These early Greek devices were technological marvels, but their use remained limited and largely tied to static warfare. The Greeks had built the weapon, but they had not yet unlocked its full potential. That task would fall to the Romans. When Rome encountered Greek artillery during its campaigns in the eastern Mediterranean, it saw not just clever machines, but strategic possibilities. Where the Greeks had built machines for occasional sieges, Rome envisioned standard-issue precision weapons tools to accompany its armies on every campaign. Weapons that could be deployed quickly, calibrated efficiently, and used both in assault and defense. The Romans took the idea of the ballista and refined it with engineering discipline, logistical foresight, and battlefield practicality. So why Rome took it seriously? When the Romans encountered Greek artillery in the 3rd and 2nd centuries BC, first in the hands of Hellenistic kingdoms like Syracuse, Macedon, and the Seleucids, they saw more than mechanical novelty. They saw a tool that fit perfectly into their military machine, adaptable, terrifying, and ideal for their methodical approach to war. Unlike the Greeks, who used torsion weapons sporadically, mainly during sieges, Rome saw their battlefield potential. As the Republic expanded eastward and faced cities fortified with massive stone walls and defenders well-versed in siege warfare, Simple ladders and rams were no longer enough. Rome needed power, reach, and precision. The ballista offered all three. In the siege of Syracuse, 214 to 212 BC, during the Second Punic War, Roman forces under Marcus Claudius Marcellus were repeatedly repelled by advanced Greek defenses, including ballistae and catapults, designed by none other than Archimedes himself. According to Livy and Plutarch, Archimedes' machines inflicted heavy Roman losses, targeting ships and men with uncanny precision. Though the city eventually fell, the siege left a lasting impression on the Roman military. Siege warfare had become an arms race. Archimedes constructed catapults to shoot at different ranges and positions. He brought great machines to bear, launching stones and bolts with astonishing accuracy. Plutarch, Life of Marcellus, 14. After witnessing such effectiveness firsthand, the Romans began systematically integrating torsion artillery into their military doctrine. By the time of Julius Caesar, ballistae were part of every major campaign, not just for siege work, but in mobile battlefield roles. In his commentary De Bello Gallico, Caesar describes using artillery during the siege of Avaricum and at Alesia, where Roman forces built an elaborate double fortification and used artillery to control the perimeter and suppress Gallic sorties. There was scarcely a place left for assault that was not protected by a battery of machines. Caesar, Gallic War, Book 7. But Rome's interest wasn't just tactical, it was philosophical. The Roman mindset revered order, discipline, and control. The ballista fit perfectly into that ethos. Unlike the chaos of slings or archers, the ballista was a mechanically consistent, mathematically optimized, and elite-operated weapon. It brought engineering into the very heart of warfare, turning combat into calculation. It was also scalable. Rome didn't just use a few heavy machines in sieges. They developed light field versions known as scorpiones and naval-mounted ballistae for ship combat. Each legion eventually had a dedicated artillery corps, the ballistari, trained in the construction, operation, and maintenance of these weapons. The presence of artillery in every Roman marching camp, often mounted on towers at the corners, turned even a temporary bivouac into a fortress. According to Vegetius, writing in the late Roman Empire, these machines remained a critical part of military preparation. No camp should be considered secure without engines of war at its angles. Vegetius, De Re Militari, Book 2. In essence, Rome took the ballista seriously because it aligned with everything the Roman army stood for: discipline, precision, preparation, and psychological dominance. Where other cultures saw siege engines as niche tools, Rome made them a pillar of battlefield supremacy. How the ballista worked? At first glance, the Roman ballista might look like a simple crossbow scaled to siege proportions. But don't be fooled, this wasn't just a bigger bow. What you're looking at is a machine of chilling precision, designed not just to launch a bolt, but to do so with terrifying speed, silence, and certainty. It began with the frame, a solid bed, often built from seasoned oak, wide and heavy enough to anchor the immense power it would soon release. Rising from it were two thick vertical pillars known as cheekpieces, shaped like the shoulders of a giant. These weren't just structural supports. Inside each stood a tightly packed torsion spring, coiled from bundles of twisted animal sinew or even human hair, soaked in vinegar to maintain elasticity and protect against decay. The more the arms were cranked backward, the tighter the sinew coils became, storing enormous potential energy. Upon release, that torsion force unwound explosively, snapping the throwing arms forward with violent torque. This was rotational force, coiled and released in an instant. These springs were the real source of the ballista's strength, not the bending of a bow, but the explosive torque stored in twisted cords. Each spring was bound by a set of bronze washers, called modioli, which acted as ancient tensioning discs. A trained ballistarius could turn these with a metal bar, tightening or loosening the coils with surgical precision. Too much tension, and the arm might snap. Too little, and the shot would lose power or veer off. The sinew bundles responded to moisture and temperature. In humid climates, sinew could swell and slacken, while in dry heat, it might shrink and tighten too much. Ballistari had to constantly adjust tension, sometimes even rewrapping the bundles during long campaigns. Getting the balance wrong meant reduced range, dangerous misfires, or snapped arms. Precision was survival. As the Roman architect Vitruvius wrote in the 1st century BC, "The holes in the frames must be made so that the length and thickness of the arms correspond with the tension." Vitruvius, De Architectura, Book 10. To a Roman engineer, every siege engine began with the projectile. Say you needed to fire a bolt measuring 90 centimeters long. Vitruvius tells us the hole cut into the frame to house the torsion spring, packed tight with sinew, should be 1/9 that length. The arms, 7/9. And so the measurements flowed outward, every element of the machine built in proportion, like a lethal equation in wood and bronze. If a bolt measured 90 centimeters, the torsion spring hole would be 10 centimeters in diameter. The arms would each be 70 centimeters long. Nothing was eyeballed. Everything was calculated. Into each spring was slotted a throwing arm, usually carved from ash or maple. Strong woods that could take the stress of rapid acceleration without splintering. These arms sat horizontally and were not pulled back like a bowstring, but instead rotated forward when released, like two levers snapping from tension. Between the arms lay a smooth, narrow groove, the canalis, or slider. This is where the iron-tipped bolt rested before firing. It wasn't just a cradle. It was a precision guide rail, keeping the missile steady as it accelerated, ensuring clean trajectory and deadly accuracy. Some later versions even used metal-lined channels for greater durability. To draw the arms back into firing position, crews used a ratcheted winch and claw mechanism mounted at the rear of the machine. It took strength and coordination, sometimes 4 men or more, to haul the arms into place. Once cocked, the machine held its breath, waiting on a simple trigger, a rotating release catch or locking peg. This wasn't just elegant, it was revolutionary. It meant that whether you were constructing a compact field ballista or a great siege piece for smashing city walls, you followed the same ratios. The dimensions scaled, but the proportions remained. This sounds simple, even abstract, but in practice it meant that every projectile size had a corresponding machine configuration, a system of standardization that prefigured modern industrial production. This allowed for parts to be manufactured in advance, transported across the empire, and assembled by trained artillery crews who had never seen that particular engine before, but knew exactly how to operate it. The ballista was not an isolated marvel. It was part of a vast living system, a weapon of engineering, yes, but even more so of planning, discipline, and logistics. Tucked among the baggage trains and camp gear of each Roman legion were the bones of machine, frames of oak, coils of twisted sinew soaked in vinegar, stacks of iron bolts, and crates of bronze washers and washers. Everything was modular, replaceable, and standardized. The ballista could be broken down into its parts and transported in pieces across mountain passes, over rivers, or through enemy forests, then reassembled in the span of a few hours by trained hands who knew every screw, spring, and pin by touch. Those hands belonged to the Ballistari, a specialized corps within the legion, not just warriors, but craftsmen, engineers, and artillerymen in uniform. Under the command of the Praefectus Fabrum, these men weren't improvising under pressure. They were executing rehearsed tasks, backed by field manuals and guided by proportions laid out a century earlier by men like Vitruvius. The Romans took this seriously. When the legion made camp as they did every evening, without exception, the artillery crews were assigned fixed stations near the corners or gates of the encampment. There, they would set up their engines not only to defend the walls, but to provide long-range suppression in open engagements. Ammunition was stacked, moisture checked, sinew cords retensioned depending on the humidity or climate. These weren't trivial factors. A single day's rain could loosen the torsion springs and reduce the machine's killing power. Even Pliny the Elder noted that Roman military engineers were deeply concerned with mathematical balance, calculating the stress load, recoil force, and torsion retention for every machine. So the Ballistarii watched the sky and felt the fibers with their hands, tightening or releasing coils the way a musician tunes strings before a performance. To the men behind the winch, it wasn't enough to know how to fire. They had to know when, how far, and under what conditions. They trained in teams, one to load the bolt, one to crank the arms, one to check the tension, one to give the signal. A single shot was the result of coordinated precision, and when it struck, it shocked. In recent decades, groups like the Ermine Street Guard in the UK and experimental archaeologists such as Dr. Peter Vemming of the Danish Medieval Center have brought the ballista back to life. Using Vitruvian proportions and ancient techniques, they've constructed full-scale working replicas to test Roman artillery performance under real-world conditions. These reconstructions allow us to see, not just theorize, how Roman ballistae functioned in battle, how fast they fired, how accurate they were, and what kind of damage they could truly inflict. With a sharp snap of unwinding sinew, the arms leapt forward, transferring all that coiled energy into the waiting bolt. It flew silently, no arching lob, no whistling slingstone. Just a straight, deadly line. At full power, it could launch a variety of projectiles depending on their size and intended role. The most common were long iron-tipped bolts, some over a meter long, designed to punch through armor, shields, or fortress gates. Tests from full-scale replicas suggest that a bolt from a heavy ballista could penetrate 2 layers of Roman-style mail armor, or even blast clean through a dense shield wall made of layered wood and hide. This made the ballista not just a siege engine, but an anti-personnel weapon capable of breaking enemy morale long before lines clashed. Lighter variants used lead-weighted darts, which offered better aerodynamics for rapid field use. In siege scenarios, some heavier ballistae were modified to hurl stones, though this was more often the domain of the onager. Modern reconstructions show that a Roman ballista could fire 2 to 4 bolts per minute, a 5 to 10 kilogram bolt at speeds exceeding 100 kilometers per hour, depending on the size of the machine and the type of projectile. These were not light projectiles. They carried the momentum of a battering ram in flight. With proper torsion, tension, and arm calibration, a bolt of this weight could travel hundreds of meters and still hit hard enough to cripple formations or batter defensive structures. In terms of range, the Roman ballista was remarkably versatile. Large siege ballistae could reach targets up to 400 to 500 meters away, useful for harassing city walls or fortifications from a distance. Smaller, portable versions, sometimes referred to as chirabalistrae, were far more accurate at short distances, delivering sniper-like shots between 100 to 200 meters, often targeting officers or exposed cavalry. Physical evidence supports these reconstructions. At Vindolanda, near Hadrian's Wall, archaeologists unearthed iron ballista bolts with pyramidal heads designed to pierce armor and bone. At Masada and Jerusalem, Dozens of stone balls and heavy projectiles were discovered in siege layers dating to the Roman campaigns of the 1st century AD. These artifacts match the specifications found in Vitruvius's treatise De Architectura, giving us a rare convergence of theory, archaeology, and experimental validation. His writings didn't just survive. They work, and the evidence proves it. Unlike a catapult that groaned and flung stones in high arcs, the ballista struck with no warning. One moment, a soldier stood in line, shield up, spear ready. The next, a massive iron bolt hissed through the air and tore through his chest, or worse, through him and the man behind him. No whistling arrow, no visible arc, just the faint crack of release, then death. Ancient sources often describe ballistae as much more than tools of destruction. They were instruments of fear. In Josephus's account of the Roman siege of Jerusalem, defenders were reportedly more terrified of the Roman engines than of the soldiers themselves. For death came swiftly and without warning. At the siege of Jerusalem in 70 AD, the Romans deployed dozens of heavy artillery engines, including ballistae and onagers, as recorded by Josephus. Some of these machines reportedly hurled stones weighing 50 kilograms or more, alongside iron bolts capable of tearing through battlements or crowds of defenders. Josephus notes the terrifying effect on the city: bodies crushed, limbs torn off, and defenders hurled from the walls by the sheer force of impact. Roman engineers often mounted smaller, more mobile ballistae or scorpiones on siege towers, allowing them to fire downward onto city walls as the towers advanced. These elevated artillery units cleared battlements of archers and defenders, softening resistance before the infantry reached the wall. Defenders knew they could be struck from above, even behind their strongest fortifications. There was no shield wall that could stop it, no cover that guaranteed safety. Even within the walls of a fortress, standing at a battlement could mean your final breath. The ballista made no distinction between front line and rear. You might be a lookout peering over a parapet or a commander directing troops from behind and still find yourself impaled in an instant. The Romans understood what we might now call shock and awe. When besieging fortified cities, they used volleys of ballista bolts and stone projectiles to shatter walls, silence archers, and psychologically break defenders. Cities under Roman siege weren't just attacked, they were overwhelmed physically and mentally. The sudden thump of massive bolts hitting stone or bone turned confident defenders into desperate survivors. Stone balls have been found with phrases like "return to sender" or "for you" carved in Latin. These were acts of psychological warfare, meant to taunt defenders and remind them that Roman justice came. The ballista's psychological effect wasn't just limited to siege warfare. In open field battles, commanders used them like ancient sniper rifles, targeting officers, standard bearers, and cavalry with surgical precision. Imagine the demoralizing sight of a tribal chieftain or centurion being struck down mid-command, his body hurled backwards, armor splintered, comrades thrown into panic. In his Gallic campaigns, Julius Caesar made use of lightweight, portable ballistae during sieges such as Gergovia and Alesia. These machines were disassembled and transported with the legions, then rapidly redeployed on hilltops or fort walls. At Alesia, Caesar's artillery played a pivotal role firing from elevated redoubts, targeting Gallic cavalry and reinforcements before they could reach the fortress. In the Roman mind, war was a calculation, and the ballista allowed them to subtract threats from the equation with terrifying ease. Elevated earthen platforms were built into the corners of the walls, where ballistae could be mounted and used for defensive fire in the event of a surprise attack. These machines could shoot across the entire front of the camp, deterring cavalry charges and night raids. The Roman navy adapted ballista technology to the sea. Scorpios and smaller ballistae were mounted on the prows of Roman warships, especially triremes and quinqueremes. These weapons were used to disable enemy ships at range, ripping sails, damaging rudders, or clearing decks before boarding. During the Battle of Actium in 31 BC, Octavian's fleet employed ship-mounted artillery, including ballistae, to strike at Antony and Cleopatra's forces before close engagement. Roman ships formed a tight artillery screen, raining bolts and stones on the larger Egyptian ships, breaking masts and sowing chaos before ramming and boarding. Witness accounts from Roman sieges and later battlefield reports suggest that ballistae disrupted formations, even when they missed. The crack of a bolt smashing into a stone wall, or the thud of impact into flesh, echoed across the field. Horses shied, men flinched, enemy lines drifted. In the chaos of pre-modern combat, where cohesion and morale often meant the difference between holding and rooting, this kind of disruption was a weapon in itself. And that was the genius of the Roman approach. The ballista didn't just kill, it controlled. It dictated movement. It made enemy soldiers think twice about standing in formation. It kept heads down on the walls. It broke rhythm. The Romans didn't need to kill every man. They just needed to break the line. The ballista helped do exactly that, with every silent shot. As the Western Roman Empire crumbled, so too did the infrastructure that kept machines like the ballista alive. The engineering schools, the trained ballistari, the standardized parts, they vanished. What followed in early medieval Europe was a crude imitation. The onager persisted longer, but siege warfare regressed. Only in the Byzantine East did a shadow remain. The chairobalistra, a compact metal-framed variant, saw limited service. But the ballista never truly disappeared. Its principles lived on. Medieval crossbows inherited its precision. Trebuchets mirrored its mechanical ambition. And centuries later, men like Leonardo da Vinci pored over Vitruvius's blueprints, drawing new visions from ancient frames. What Rome built became the foundation others would rediscover. So what made the ballista feel like secret tech? It wasn't brute force. It was calculated lethality. A ballista was sniper artillery in an age of chaos. But it demanded more than materials. It needed engineers, mathematicians, and a culture that valued logistics and discipline. Many civilizations had the idea, but only Rome had the machinery, both human and industrial, to make it battlefield ready. And that's where its legacy lies. Because the ballista wasn't just a siege weapon. It was a symbol of Rome's philosophy, a fusion of science, fear, and efficiency. Thank you for staying with us through this 30-minute journey into ancient firepower. If you enjoyed this video, please leave a comment. We'd love to know what you think.